Hello, and welcome back to the course on quantum mechanics. We are now on the sixth chapter for this course, which will be all about the time-independent perturbation theory. So basically, we will now introduce some very small perturbations or minor fluctuations or corrections in the potential energy of our system, and we will build upon the known solutions, known wave functions, and known energies of the systems that we have discussed before, such as particles trapped in infinite square wave potential, harmonic oscillator, delta function potential, and so on. So before we start with the first lesson of this chapter, let us first review some concepts. So we have discussed about the time-independent Schrödinger equation, which is just this eigenvalue equation. So the Hamiltonian operator, which is Hermitian, acting on the wave function, will give you the energy eigenvalues. And the Hamiltonian is just the kinetic energy operator plus the potential energy operator. So for the first lesson of this chapter, we'll be discussing about the first-order non-degenerate perturbation theory. So we'll first consider the non-degenerate case, meaning there's one state, one wave function per energy level. So let's first discuss what is a perturbation. So a perturbation is basically an additional energy of a system. It usually is the interaction energy of the system. So in the previous chapters, we have discussed about two particle systems or three particle system or many particle systems. And our assumption in the problems in the previous chapters is that the particles are not interacting. So if they are not interacting, this is the Hamiltonian of the system, the kinetic energy plus the potential energy, to where usually this is where the particles are trapped. If you can be an infinite square wave potential energy, harmonic oscillator potential energy, or the delta function potential energy. So we call this the unperturbed system. This is the ideal system. We know the solutions. We know the wave functions and the energy for particles trapped in these unperturbed systems. Now, if the particles now have an interaction, so their Hamiltonian now, their total energy will now be the original unperturbed Hamiltonian plus the interaction potential energy. And this system is now said to be a perturbed system. So, according to perturbation theory, we can get the new wave functions and the new energy levels using perturbation theory. And basically, it's just an approximation. So we can find approximate solutions to the perturbed system or the perturbed problem by building on the known exact solutions of the unperturbed case. So since we already know the solutions to the unperturbed case, and since the perturbation usually is just very small as compared to the original potential, then we can approximate. We can approximate the solutions up to a certain order. So this is the eigenvalue equation, the time-independent Schrödinger equation for the unperturbed system. The quantities with the power 0 pertains to the unperturbed case. So suppose this is the wave function of your unperturbed system, and you perturb the system. You add some interaction potential energy, or you slightly disturb the system, such that it will now have a new Hamiltonian, it will now have a new wave function and new energy levels. So the new Hamiltonian is just the original Hamiltonian, the original total energy of the system, plus lambda. Lambda is just an integer or a number. And h prime here is what we call the perturbation. And it's usually very, very small. A very small perturbation energy, h prime. So the perturbation Hamiltonian or perturbation energy, and it's usually very small. So the effect of this perturbation is to slightly change the wave function of the system, and we can actually approximate the new wave function and new energy of the system via a power expansion. So a power expansion in lambda. So the new wave functions is just the original wave functions, the unperturbed wave functions, plus the first order correction, second order correction, third order, and so on. Similarly, for energy, we can do a power series expansion. So again, the first terms here in the expansion are the unperturbed case, unperturbed wave function, unperturbed energy. We usually call that the zero order correction. And the second term here are the first order corrections in energy. And the third terms are the second order correction, and so on. So we substitute this wave function, to our Schrödinger equation here. Similarly with our energy, we substitute that here, and we group the powers with lambda. We group the same powers of lambda. For the same powers for lambda to the power of 0, or the zero order correction, you will just get this unperturbed system. But if you group the powers of lambda to the power of 1, you will get our first order theory equation. So if you group all of the powers lambda of lambda to the power of 1, you get this equation. Now you can actually prove that this equation, this term here, is just equivalent to this term here, and that reduces your first order theory equation to just a simple eigenvalue equation, where our operator is the perturbation H prime acting on the unperturbed states, and it will produce energy eigenvalues, which is just En1, or the first order correction in energy. So the first order correction in energy is now given by this equation. So this is actually just the expectation value of the perturbation in the unperturbed states. So from here, if you want to get the energy levels of the perturbed system only up to the first order correction, then you just add the zero order plus the first order correction, and we can always we'll just set lambda equal to 1, so that the expansion will just be no longer containing any value of lambda. So this is now the energy of the perturbed system up to the first order correction. So of course, if you want to get very accurate, you need higher order correction. You need the second order, third order, fourth order, and so on. But in this chapter, we'll only consider up to the second order correction. So if you don't know explicitly the perturbation H prime, we can just get it by, if you know the final Hamiltonian of the system and the initial unperturbed Hamiltonian of the system, the difference of that is the perturbation. For the first order correction in energy, this is now psi n1, the first order correction in energy. So therefore, the wave functions of the perturbed system is just the unperturbed wave function plus the first order correction psi n1, first order correction in the wave function. And the first order correction in the wave function is actually a summation of L. Take note, this is L not equal to N. You have psi L0 H prime psi N0, En0 minus El0. These are the energy levels. And you have psi L0. So you will notice that it's just a linear combination of unperturbed states. So because psi L0 to the power of 0, these are unperturbed state, the zero order correction. And this whole term here is basically just a coefficient. So basically, you have a linear combination of unperturbed states, and that will make the final wave function of the perturbed system as just basically a linear combination of unperturbed states. Okay. Example number 1. Let's go directly to an example. The first example is a perturbed infinite square well potential. So this is now our new system. So find the wave functions and energy levels up to first order correction for a particle trapped in this perturbed infinite square wave potential energy. So originally, in our original unperturbed case, this is actually zero the potential is actually zero from 0 to A, and infinite beyond 0 and beyond A. But in this case, from 0 to A, there's now a potential. It's now U naught. So this potential now U naught, instead of 0, we get U naught. So the floor of our square well is now raised by a value of U naught. And this now can be considered as a perturbation, because originally you have 0 potential energy, but now you have a U naught potential energy. So this is our perturbation, where U naught is a constant value of potential energy. So if you will recall, these are the unperturbed energy levels of our system: En 0, n squared pi squared h bar squared over 2 ma squared, and these are the unperturbed wave functions: square root of 2 over a sine n pi x over a, where n starts from 1 to infinity. So the ground state is n is equal to 1, psi 1 0, and the corresponding ground state energy is E1 0. You will get n is equal to 1 here for the ground state. Okay, sorry. So if we wanna get the first order correction in energy, then we need this equation. So we need to sandwich our perturbation in this inner product here. So from our the first order correction will now be En1, and then you have psi 0. These are our unperturbed case. I'm just gonna go to my board work mode. Oh, sorry. So you have En1 first order correction, psi 0, h prime, psi 0. So h prime, our perturbation is just a constant, U naught, meaning if it's just a constant, it's not technical an operator. You can take it out of the inner product. So you will get U naught, psi 0, psi 0. And orthonormality condition, psi 0, they have the same subscript, then it's just equal to 1. So meaning the first order correction in energy is just equivalent to U naught. So meaning if you wanna get the energy, the new energies of this perturbed system up to the first order correction, then it's just the unperturbed, the zero order correction plus the first order correction, which is U naught. So that one, this is the zero order correction plus the first order correction. So if you have a constant perturbation, higher order corrections will actually vanish, and the energy levels is up to the first order correction exactly. So in this case, if you have a constant perturbation, then this is now the final answer. The higher order, the second order, the third order, the fourth order corrections are all zero. That only happens when the perturbation is a constant, such as in this case. Now, how about the wave function up to the first order? What is the first order correction in wave function? Now, if you will recall the formula for the first order correction in wave function, so this is the one. And take note, this is a summation of L not equal to N. So meaning L must not be equal to N. Now, H prime, our H prime in this case is U naught. It's a constant, so we can take it out of the integral. And you will be left with psi L, psi N. So orthonormality condition states that if L is not equal to N, such as in this case, then it's equal to 0. So in this case, the zero order corrections will actually, or the first order correction will actually be 0. So that one. So there's no first order correction. So meaning the wave function of the perturbed system is exactly the unperturbed wave functions psi and 0. So that's the property if your perturbation is constant. There's no first order correction in the wave function, and your energy levels are only up to the first order correction. Okay, next example. Okay, this is still an infinite square wave potential, but these are now the new potential energies. So the system is now perturbed, but not the whole well is perturbed. Only half of the well is perturbed. So from 0 to A over 2, the potential is U naught, but from A over 2 to A, the potential is 0. And beyond A and beyond 0, it's infinite. So only half of the well is perturbed. So again, these are the original or unperturbed energy levels, n squared, pi squared, h bar squared over 2 ma squared. So we are only asked to find the energy levels up to first order correction. We are not trying to find the wave function here, only the energy levels. So we only need to get the first order correction in energy in order to find the final energy level of the system. Okay, so in this case, if you will recall, from our when we discussed about the inner product, if you have psi L, psi M, it's basically psi L conjugate. This is the Dirac notation. This is the integral form of this inner product. So you have psi L conjugate, the function in the bra is conjugated, and then psi M dx, for example, dx. And this is integrated over all possible values of x. So in a usual infinite square potential, the limits are from 0 to a, because the wave function is only defined from 0 to a. Beyond a, the wave function is 0. There's no probability of the particle being there, so psi is 0. Same with below 0. The wave function there is also 0. So the limit will just be from 0 to a. Now, in our case, we will have something like this, an expectation value of a quantity q. So it will just look like this. Now, our q here is our perturbation, and our perturbation is only defined from 0 to a over 2. It's not from 0 to a. So we cannot automatically use the orthonormality condition, which is just the Kronecker delta Lm. So we cannot use that one because our limits is not from 0 to a. So the perturbation only is from 0 to a over 2. So our h prime is actually still u naught, but its limit, the perturbation, is only from 0 to a over 2. So when we solve for the first order correction, I'm just gonna go to my board mode. So when we solve for the first order correction, en1, we have psi n0, h prime, psi n0. If h prime is not for all space, it's only for a certain limit, then you don't automatically use the Kronecker delta orthonormality condition. You need to convert this into the integral form. So basically, this is psi n0 conjugate. Our h prime here is u naught. You have psi n0 dx. This is, so the limit, if the limit is from 0 to a, then you can use the orthonormality condition. But the limit here is from 0 to a over 2. So we have psi n0, that's square root of 2 over a. There's a square root of 2 over a. So you will have 2 over a. u naught is just a constant. You take it out of the integral, and then you have an integral of so this is sine n pi x over a, this is sine n pi x over a. So basically you will have sine n pi x over a squared or sine squared. So that one. So you will get an integral of sine squared. So I will give this integral to you. The answer of this is a over 4. And you will get the first order correction as a is cancelled. You have 2 over 4 or 1/2. So u naught over 2. So this is now the first order correction. It's u naught over 2. So meaning, if you approximate the energy of this perturbed system, it will just be this one, the unperturbed energy levels, plus this one, the first order correction. That one. But in this case, this is not accurate. You will actually need a higher order correction, because the potential, our h prime here is not constant all throughout the well, because h prime here is u naught, but the h prime here is 0. So it's not the same. The h prime is not the same all throughout the well. So again, h prime here is u naught, but h prime here is 0. There's no h prime. So in that case, if you don't have a constant h prime, you will need higher order correction. So this is not pretty much accurate. But if you are only required up to the first order correction, then this is already enough.
Daddy.
So another example. So we have still an infinite square well potential, but we perturb it with a delta function. So there's a delta function in the middle of the well. So instead of from 0 to a, the potential is 0, there is a delta function with strength alpha at x is equal to a over 2. So at the center of the well. So what happens now to, or you are asked to find the first order correction in energy and the ground state. And you only show the first 3 non-zero terms of a particle trapped in this perturbed infinite square well potential energy. Okay, sorry. So for the first order corrections in energy, En1, so this is just equivalent to the unperturbed wave functions h prime psi n 0. So our h prime here is our delta function. So it's a positive delta function. No? So it's not a well, it's not a delta function well, but it's a delta function barrier. So you have alpha delta x minus a over 2. Okay. Now in this case, this is not a constant again, so we will need to convert this inner product into the integral form. So you will get psi n 0. Psi n 0 is square root of 2 over a. So you will get 2 over a. There's a square root of 2 over a factor here, square root of 2 over a. There's an alpha, so you will have 2 alpha over a. And then integral of, you have sine. There's a sine n pi x over a here. Sine n pi x over a here. So basically, conjugate of that is just itself, because it's a real function in this case. So you have sine squared n pi x over a. You have 2 sine n pi x over a. So this is from 0 to a. And we have our delta function, x minus a over 2 dx. So again, it's very easy. Don't be afraid of the delta function. If you see a delta function in your integral, you must be very happy. You must rejoice, because you don't need to integrate. So this will become 2 alpha over a, and the value of sine squared at x is equal to a over 2. So sine squared a over 2, so n pi over 2. Sine squared of n pi over 2. That one. So no integration needed if you have a delta function. Now, the value of this sine function, sine squared function, is either 1 or 0. So this is 1 if n is odd. This is 0 if n is even. So meaning the value of the first order correction is 2 alpha over a if n is odd, and it's 0 if n is even. So going back to our case, our first order correction in energy is this one. So what does this mean? This means that only odd energy levels have a first order correction in energy. So meaning E1, the ground state, will have a correction of 2 alpha over a, but the first excited state E2 will not have a first order correction. So if n is even, there's no first order correction. So on for E3, it will have the same energy level. So if you will look at this from an energy level point of view, if these are the original unperturbed energy levels, this is E1 0, E2 0, this is E3 0. Then when you perturb the system with this perturbation, only the odd energy levels are lifted. So meaning E3 will now be this one, E2 will still be the same, and E1 will also be lifted. That one. So only the odd energy levels are lifted by an amount of 2 alpha over a. So that is the significance. Okay, how about the ground state? The ground first order correction in the ground state. Okay, sorry. Only show the first 3 non-zero terms. So if you will recall, this is the equation. So for the ground state, that is n is equal to 1. So we have psi 1, 1. So psi 1, 1. Let's go back to my board work mode. So the ground state correction is psi 1, 1. And this is summation of L not equal to n. So n is equal to 1. Then you will have psi L0 H prime psi N0 over En0 minus El0. That one. Sorry, there should be a psi L0 here. Sorry. Okay, so it's a linear combination of the unperturbed states. Okay, so in this case, let us first okay, by the way, in this summation, this means that L is not equal to 1, and since n can only have values of odd numbers and excluding 1, meaning L will start from 3, next is 5, 7, and so on. So that one. So let's first try to find this one, this inner product, psi L0 H prime psi N 0. So we have psi L0 H prime psi N0. We convert this into the integral form. So this is basically, so psi L is square root of 2 over a sine, if you will recall, the wave functions for an infinite square wave potential energy looks like this. So if you have a subscript L, meaning you have sine L pi x here. Okay, so you will have, there's a square root of 2 over a here, square root of 2 over a here. Our h prime here is the delta function. There's an alpha, so you will have 2 alpha over a. Integral of sine L pi x over a. This is psi L0. And then the delta function is in between them, x minus a over 2. And then sine n pi x over a dx from 0 to a. Again, if you have a delta function, in the delta function inside your integral, then you're in luck. You don't need to integrate. So it's just the value of these two signs at x is equal to a over 2. and you will get sorry, this is the ground state. N is equal to 1, so meaning this is 1. This is also equal to 1. Sorry, this is 1, so meaning this is 1, so this is just sine pi x over a, and you will get a value of 2 alpha over a sine L pi over 2. So again, the value of sine L pi over 2 is either 1 or 0. So if L is even, then this sine term is 0. And if L is odd, then the value of this is 1. Not necessarily 1. It's either 1 or negative 1. But the value of L, so meaning the value of L only starts from 3, because L is not equal to 1. So 3, 5, 7, and so on. So that one. And we already know this one in the numerator, and in the denominator you have E10 minus EL0. Again, the energy levels is this one, n squared pi squared h bar squared. So meaning E10 is, for n is equal to 1, it's just pi squared h bar squared over 2m squared, and EL0, so you replace n by L, so you have L squared pi squared, and you will get a value of 1 minus L squared pi squared h bar squared over 2m a squared. So you substitute this one in the denominator here and this one in the numerator here, and expand up to the first 3 terms. So the first term is 3, so meaning you will get psi 3, 0. The second term is 5, so meaning you will get psi 5. And the third term is 7, you will get psi 7. So you do that, and you will get these results. So these are now the first order correction in the ground state wave function. The ground state, or the wave function for the ground state. So the first term again is 3, psi 3, so you have 3 pi x, psi 5, psi 7, and so on. So that's it for this problem. Okay, for the last example for this lesson, we have identical bosons in infinite square potential. So when we discuss about this is a two-particle system, so you have 2 identical bosons trapped in an infinite square potential. And when we discussed about this system in the previous chapter, we avoid the interaction. We assume that they are not interacting. But now, in this case, they now have an interaction potential energy. So it's negative a u naught the delta function x1 minus x2. Meaning, the 2 particles, the 2 identical bosons, will only interact if x1 is equal to x2. Meaning, if they are both in the same point or in the same location. And in that case, the potential energy, if they are in the same point, is negative a u naught, where u naught and a are both constants. Okay. So, this now, the interaction potential energy is basically our perturbation. This is now the additional energy of our system. So, in addition to our original Hamiltonian. Now, if you have a 2-particle system, and since this is infinite square wave potential, you just add the 2 energies of the 2 particles. So you have n1 squared pi squared h bar squared over 2m squared plus n2 squared, and you will get this one. So meaning, we are asked to find the ground state and the first excited state energies after the first order correction. So what is first? So first things first, we need to find the unperturbed energy. So the unperturbed ground state is when n1 and n2 is equal to 1, when both of the particles are in the ground state. And in that case, that is E11, 0. And you will get this value, pi squared h bar squared over ma squared. The second excited state, the first excited state is when one particle is in the ground state and the second particle is in the first excited state, or in E2, or psi 2 rather. So one is in state psi 1 and the second one is in state psi 2, and you will get from this equation this one. These are now the unperturbed energy levels. Now, if you will recall, for a 2-particle system, the wave function of a 2-particle system if they are identical bosons depends on if the two particles are in the same state or in a different state. If they are in the same state, then you just multiply the two wave functions. But if they are in a different state, then you need to take into account all the possible combinations. So what if particle 1 is in state psi A, particle 2 is in state psi B, and the reverse? What if particle 1 is in state psi B and particle 2 is in state psi A? So from here, the ground state, this is the ground state energy, meaning both particles are in psi 1. So you'll just get this one. So you will have square root of 2 over A. There are two square root of 2 over A, so you will just get 2 over A, sine pi x1 over A, sine pi x2 over A. So this is now the ground state, unperturbed ground state. And the first excited state, since both of the particles are in different states, so we use this equation. So you have this is basically psi A, psi B, psi B, psi A for particle 1 and 2 respectively. So this is now the unperturbed energies for the ground state and the first excited state, and this is the unperturbed ground state and unperturbed first excited state. So how do we find now the corrections? So for the corrections, so for the first order correction in the ground state, so this is the ground state. So we sandwich our perturbation, which is this one, with respect to the wave functions of the ground state to get the first order correction in the ground state. So basically, for the first order correction in the ground state, sorry, this should be board work mode. So you will have E11, this is the ground state and first order correction of the ground state. So this is, you have the ground state psi 110, and then the perturbation H prime, and then you have psi 110. So you put your perturbation in between the ground states to get the ground state correction. Similarly, for the first excited state correction, you have 1, 2. So you use the first excited state here, 1, 2, psi 1, 2, and psi 1, 2 here. So our H prime is negative A unit, the delta function x1 minus x2. Okay, again, we need to convert this into the integral form. So you will have, this will have a constant square root of 2 over A, square root of 2 over A, and there's an A here. Sorry, our ground state, sorry, if you will recall, this is our ground state, this one. So you have, in our equation, you will need two ground states in the integral. So basically, you will get 2 over A squared. So 2 over A squared. And then this one, square of both of these terms. Okay. So you will get 2 over A squared, and then there's a factor here, negative A unit. So negative A unit. And in the integral, you will have sine pi x1 over A, sine squared, and sine squared of pi x2 over A. And then the Dirac delta function, x1 minus x2. And this is dx1, dx2. Okay, so you first integrate over dx1. So your integral will be this one. In your integral, it will involve this term, sine squared pi x1, and then the Dirac delta function and x1. This is a double integral since we have two differential measures here, x1 and x2. So both x1 and x2 are evaluated. Since this is an infinite square wave potential, they're all evaluated from 0 to A. So this is a double integral from 0 to A. 0 to A. Now, for the first integration, we integrate over x1. So all terms that contains x1. So this doesn't contain x1, so this is out of the integration. And again, there's a Dirac delta function here. So you don't need to integrate. This will just force this to have a value of x1 equal to x2. And you will get negative 4 unit A, integral from 0 to A, of sine to the 4 pi x2 over a dx2. Okay, so I will just leave the this integration to you. Look for table of integrals, sine to the 4th. What is the integral of sine to the 4th du? Sine to the 4th u du. And this will give you a value of -3/2 u naught. So this is now the first order correction in energy. For the second order, the first order correction in, this is the first order correction in the ground state energy. For the first order correction of the first excited state energy, E1 to 1, you do the same, but you use the first excited state. So 1 to 0, H prime psi 1 to 0. So that one. So I will leave this as an exercise for you. So in this case, our first order corrections in the ground state energy will be -3/2 u naught. So meaning, if you are asked to find the energy, the new ground state energy up to first order correction, so it's just the ground state energy, this one, the unperturbed ground state energy, plus the first order correction. So that one, -3/2 u naught. So this is the perturbed ground state energy, and for if you do it correctly, you will get the first order correction in the first excited state energy as -2 u naught. Meaning, if you approximate the first excited state energy up to the first order correction, you will get this one. So this is not the perturbed first excited state energy up to the first order correction. Okay. So that is it for the first order theory, but this is still the non-degenerate case. So for the next lesson, we will still be discussing non-degenerate perturbation theory, but now for the second order correction. So I will see you again in the next lesson.